So, how many of you guys have played with Legos?
Every day.
Every day. Every day.
Hey, I got 11 boys, son.
How many of you guys have played with Minecraft? Ever played Minecraft?
Oh yeah, I'm sure it's good.
Yeah, Minecraft is a really cool little video game. The reason I'm bringing it up is it's like Legos. There's only one or two or maybe a half a dozen blocks, right? You can pretty much make blocks and throw them away. And then there's a few other things. But as games go, it's not very complicated. Just like Legos. When Legos started, they weren't very complicated at all. They were like blocks, and they fit together. And they were bright colors. You could eat them and chew them. And that was about it. The neat thing about them was they fit. They held on to each other. And you could build anything. If you had enough Legos, you could build anything. These days, it's still the truth. You can still get simple Lego blocks. Go to the Lego store, you can get them by the bucket load. Have you guys ever been to a Brick Fest? Oh man, if you like Legos, go to a Brick Fest.
In downtown Beaverton, they got a Lego store. It's not owned. It's a used brick store. But it's all Legos and they're all used. And you've got these little tubs that you pay for by the tub. And
Yeah.
you can go through his little table. It's about this big. It's 8 inches deep. Pick out the one you want. He's got 500 or 600 Star Wars characters. And I mean, he's got like display cases of Star Wars people. So
Legos are fun. Now, why am I talking about Legos? Because, well, we talked last time about how software was pretty complicated. But the thing about it is, it's not complicated at the bottom level. I mean, like stuff like philosophy, that's complicated all the way down. I mean, if you start thinking about what's truth, what's beauty, what's justice, yikes, who knows? The thing about computers is you go down far enough and it's just 1 + 1 = 2. It's just numbers and addition and real simple things like, it's like Legos. Little blocks that fit together. You fit them together, you get enough blocks and it gets complicated. Then like we said on last time, you just take that whole thing and you just treat it as one black box. You just treat it as a sub-assembly and you forget about it. Engines are complicated, like Rod said the other day. But for some people, like my son, he'll go over to a friend's house and they'll drop a new engine in a car. And all that matters to him is whether the thing mounts on the same blocks or whether they have to fab new blocks. And whether it hooks up to the tranny or what they have to do to make it hook up. Anything that's complicated can be what they call abstracted. You just say that this whole thing here, it's just one thing. And it works like this, and I'm going to forget about how it works on the inside. So today what we're going to do is we're going to talk about programming languages, but we're going to build them up from the bottom up so that you understand what the Lego blocks look like. Now the neat thing about software is you don't have to buy Lego blocks. And that store sounds great. At Brick Fest you can buy Lego blocks by the pound, and there's lots of blocks in a pound. Lots of blocks. Today the simplest languages are all very simple. They're like the old style Lego blocks, 2 by 3, you know, they're just standard height. You do adds, subtracts, you assign values to variables, it's real simple. Modern languages are more like modern Legos. They have specialized little statements in them and little blocks that you look at that and you think, what the heck is that? You say, oh, well, that's the tip of Java Fett's tail. That's what that block is. You only use it in 1 or 2 sets. We're going to only talk about the simple statements that really much you'll find in any language. And you'll use them for your assignment in making a real simple JavaScript program. So let's get started. Let's build it up from the bottom up. So we said before that any system has inputs and outputs, and the system itself has a process. The other thing that systems have are memory. They remember things. We said yesterday that Tuesday we said that inputs and outputs can be real complicated. They can be sensors, they can be electrical signals, they can be concepts. I have a piece of software now that asks somebody, how confident are you that you can do this thing? And we take that confidence as an input. And we change how we interact with the person based on how confident they think they are. The bottom level, any of these inputs get translated into numbers. They're all just numbers. Now you think, well, just numbers. But the neat thing is, numbers represent everything. Everything physical. I'm not going to say that numbers can represent justice or numbers can represent truth or beauty or God or whatever that is. But anything in the physical world can be represented by a number. You just have to name it the right way. In our human experience, we use base 10. So what's base 10? Tell me what base 10 refers to.
Yeah, 1 through 10 and start at number.
1 through 10? Back there?
Yes.
Decimal numbers? That's right, decimal digits. We happen to have 10 of these things, so we based our number system on it. You said 1 through 10. I'm going to say 0 through 9. We have numerals that go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If you want to go beyond 9, you take that one digit, 0 through 9, and you carry it over, and you now have another digit. This digit represents how many tens you have, right? These are tens. I know we're going back to second grade here, but I want to cover the basics. I'm not trying to insult you by telling you you don't understand numbers. Tens, hundreds. This is basically 1 to the 0 power, 1 to the first power. Nope, I'm wrong there, aren't I? Off by 1. 1 squared. No. Yeah. I should recurse, shouldn't I? 10 to the 0, 10 to the 1, 10 to the squared. Hundreds is 10 squared. 10 to the third. So this digit is my 0 digit, this digit is my first digit, this is my second, this is my third. That's decimal numbers. Computers, lucky for us, are really stupid. And they just deal with on or off. They just deal with on or off. So they only know 2 digits. They only know 2 numerals, 0 and 1. There's only 0 and 1. 0 typically means off or false, or on, or true, true. There's a third number, which we hid in our databases. A number that isn't true and isn't false, isn't on, isn't off. Sometimes in our databases we called it nil. Sometimes you'll call it not a number. But that means there's nothing here. It's not even 0. I don't even know what it is. Just move along. There's nothing to see here. Let's see. How do we start with these zeros and ones. The reason we use zeros and ones is because it works even in the roughest environment. You know, it's real clear to tell if the light's on or off. Sometimes it's hard to tell if the light's half on, half off. There's no gray in this area. It's just black and white. So we're going to take this idea of powers of 10, and we're going to use them in a binary or a power of 2 situation. So in our bottom level, it can be either 0 or 1, and that's 2 to the 0. Our second digit can be 0 or 1, and that's 2 to the first power. Our third digit, 2 to the third power. So if I'm counting from 0, this is 0, this is 0, this is 0. I'm not Norwegian. I tend to put slashes through zeros so I can tell the difference between zeros and O's. Do a lot of coding, you mess up a lot with zeros and O's. So if I want to represent 1, then I put 1 here. And I've run out of numbers. So all the numbers I can put in that place. So if I want to go to 2, I have to roll over to 0 again, just like I roll over from 9 to 0 when I'm counting in base 10. And then I put a 1 here. So 2 in binary is 0, 1, 0. If I go to 3, yada, yada, yada. I'm sure you catch the pattern now. Why is this important to programming? Well, it's important to programming because at the bottom, everything's one of these numbers. This is a 3-bit number. If we wanted to make it a 4-bit number, 2 to the 4, we add zeros. What we find is when we get to, let's see, what would 9 be? 9 is 8 plus 1, right? So that a 9 would be 1, 0, 0, 1. There's an 8. This is a 4, there's no 4s. This is a 2, there's no 2. So 8 plus 1 is 9. Well, if I add 1 to 9, I need another symbol for that. 0, 1, 0. We don't have a numeral for that in base 10. So we just go to a letter. We use usually, well, it used to be a capital letter, but these days it could be lowercase letter. I'm going to use a capital letter. This is the number A. It's not the letter A, it's the number A. And if I'm going to use 4 bits, 1, 2, 3, 4, I go all the way up to the number F. 1, 1, 1. That's the number F. These 4-bit numbers are called hexadecimal. Hexadecimal, meaning base, there's 16 of them. Hexadecimal. 4 bits can go from 0 to F, or in base 10, 0 to 15. There are 16 numbers there. There are 16 possible values. They go from 0 to 15. In computers, we always count from 0. Always count from 0. This is a major head bender. Most people don't count from 0, they count from 1. That's the first time I do something, it must be 1. In computers, you count from 0 a lot. It's one of the little tiny things that'll cause bugs for you. Because you think, wait, this thing started out wrong. How come I thought it would go 16 times, but this number's only 15? What's going on? It's because in software, we start from 0. The first semiconductor-based computer, the Intel 4004, was for a calculator. It was built in the 70s.
Is this an A?
That's an A.
Which means what?
It means 10 things, except it's in the hexadecimal notation. 0, 1, 2, 3, 4, 5, 6, 7, 9, plus 1 is A, plus 2 is B, C, D, E, F. If I use 8 bits, that was the size of the first breakthrough microprocessor, was the Intel 8008. And after that, the one that really busted the whole thing loose was the Intel 8080. That was in 1975. At that point, you had a complete computer on a chip. What used to be 6-foot racks, thousands of vacuum tubes now fit in a little tiny chip. The whole thing changed at that point. 8 bits can carry from 2 to the 0 all the way up to 2 to the 8. They're 8 bits. Yes, sir?
Excuse me, shouldn't there be a 2 to the second?
Oh, thank you.
Sorry.
Thank you very much.
Yeah, I was
Yeah.
confused at first. thinking that was the
Very good. Keep an eye on me. I don't know what I'm talking about.
Oh, it's good.
I don't have a black marker that works anymore. So for 8 bits, I can store how many numbers from 0 to F. Because I got 2 nibbles in 1 byte. And that's from 0 to 255. In general, if I have 16 bits, I can store up to 2 to the 16 minus 1. I can store a number that big. These days, most processors have how many bits? Anybody know? 64 bits. That's a big number. 64 bits is what, 6 billion something or other? I don't know. So when you look inside a computer down at the hardware level, all the numbers are stored in terms of these bits. Down at a hardware level, I'm worried about 1 bit at a time. I'm dealing with bytes. These are 8 bits in a byte. A byte equals 8 bits. In a simple processor these days, they're mostly 16-bit or 8-bit processors. If I store a number in a computer, I can store it in a memory location, or I can store it in something called a register. A register. I don't know where that comes from. Why you would store a number in a register.
Like starting money right now.
Yeah, maybe. You look in a register drawer and you got those little pockets for different kinds of money. It's a good analogy. Inside a computer, inside a central or a computational processing unit, it used to be called the central processing unit. Now there are so many multiprocessors, it's the computational processing unit, the CPU. It contains a bunch of registers. Now the cool thing is here, the numbers not only represent inputs, so I'm storing my inputs, I'm converting them to numbers, I'm storing them in these hexadecimal numbers, but I'm also storing what should I do as numbers. These are called instructions. Machines understand instructions. And instructions are numbers too. Sometimes instructions are called operators. I'm not going to hit the thing here and try to get this a little more. So an operator is something like and, or plus, or add. So a simple instruction is add this number to that number. A real simple instruction is do the next instruction. At the bottom level, CPUs are so stupid. But that's cool. All they have to do, they're like little Lego blocks. All they have to do is one thing and one thing well. They have to do their operator, and they have to operate on other numbers. Those, can you read this? Is this too low?
Oh, no, it's fine. I need to.
I got one more. Operand. Remember tuple? Remember some of the other weird language words we use? These are the weird language of machine code. So at its very basic level, I've got hex numbers. You write a hex number using 0x and then the number. So like 0xFF, that's equal to 255. You see a little 10 there? That means base 10. The 0x tells you this is base 16. If you're reading machine code, you know, like in The Matrix, in the movie The Matrix, all that stuff flittering down the screen, that represents, in an artistic way, the machine code, the underlying code of the universe, of the simulation that is The Matrix. If you look at the underlying code of computers, it's not as cute looking. Let's see if we can quickly get a picture of machine code. I remember this stuff. This is great. So, this is machine code. It's just a bunch of hex numbers. It's just a bunch of hex numbers. This is called a machine code dump. And when you're operating, when you're working at the hardware level with microprocessors, you can actually read this stuff. It's It's not mystical or anything like that. You've just done it so often that it's second nature. The other thing you can do when you're working at the machine code level is you can do machine code arithmetic. You can see, oh, that's the operator, oh, and that's the operator, and that's the other operator, and I'm going to add them together. You spend enough time in here, and you can actually read this stuff. It's not that hard. Here's an example of, as you might imagine, it's not your strongest suit to be able to read this stuff, to look at a bunch of numbers and interpret it. So we cut you some slack, and we take these instructions and these operands, and we make simple little words for them. So let's summarize where we're at here. At the bottom, and I'm going to write the bottom at the top, we've got numbers. Then the numbers come together to become machine code. Machine code is numbers. Numbers for instructions, numbers for operands, numbers for operators. Machine code is stuff like add this number to that number, and it's all in hexadecimal. The next layer up is assembly code. If you don't like dealing with numbers, you're not alone. Nobody likes dealing with numbers. Assembly code looks like this. Assembly code is simple numbers that represent, or I'm sorry, simple words that represent these numbers. Every machine has a different kind of assembly code. So an Intel machine has different machine code than a Motorola machine. If you've got an old Mac, it uses a PowerPC architecture. That word architecture means that it's got a different kind of set of registers and it's got different instructions than an Intel machine does. Register architecture says that I have basic instructions that are different. And if you're a hardware engineer, you learn this stuff and you compare architectures, and some of them are better than others. It's one of those levels of detail that are important if you're down at the very bottom. Who here plays video games? How many times have you kept your drivers up to date? Oh, you should. The buggy stuff, the stuff that causes your machine to crash is usually a bad driver. You're constantly updating your drivers. Drivers are the code that talk directly to the hardware. They make your graphics card sing and dance and work really fast. If you're a driver writer, if you write drivers, you oftentimes write in assembly code. Because you need to be right down on the hardware. You need to know exactly which bits are being set, where they're going. It's a different kind of thinking. I used to write this stuff all the time. A guy who's good at this, frankly, thinks different than the rest of us. They just think different. And they're really good at a certain kind of thinking. And if you find that that's fun for you, it's worth a lot of money. I knew two guys in my early career. One guy's name was Milton, who works for IBM now. He was really good at assembler code. He was really good at working at a very detailed level, but also carrying the big picture in his head at the same time. He understood hardware and he understood software. Again, if you're a senior engineer and you work at this level, you can pretty much charge what you want. It's one of those specializations, like if you're really good at Intel processors, everybody's writing drivers in Intel. If you're good at some of the low-end, they're ARM processors, ARM processors. Now, the processors in an iPhone are all ARM processors. The processor in an Arduino is an ARM processor. Okay, the big deal here is I'm using symbols. I'm using words instead of numbers. that's the step from machine code to assembly code, is I use symbols or words instead of numbers. And I use a tool called an assembler to change those words into numbers, and then I hand the numbers to the machine, and the machine executes the numbers. Everything comes down to numbers. These symbols represent variables. What's a variable? Go cover that in a minute.
Wait, so assembly code uses words and machine code uses numbers?
Yep. Yep. Now, if you look at a program written in assembly code, there isn't much to this. Load 1, load 2, what the heck is that? Branch, what the heck is that? So you'll see in assembly code, well-written assembly code has a lot of comments. This is a comment symbol. The assembler goes through here and says, oh, I know what a load is. That means this number, 0A, 0X. Oh, there's another number. I'll load that number. So an assembler is going through and it's translating each one of these things into a number and throwing it at the machine. That's what an assembler tool does. If it gets to this number, if it gets to this hash mark, it knows it's done and it can ignore the rest of this. This side is for the humans. This is for the programmer to tell the story of what the code is doing for the next human that has to work on it. Sometimes that next human is the same guy who wrote it, except it's a couple weeks later and nobody remembers code very well. It's not like somebody's face. Your head isn't set up to remember this stuff like it's set up to remember smells or it's set up to remember faces. So you leave yourself lots of comments. This code is kind of hard to read. It's hard for anyone, even the guy who wrote it, to look at this and say, oh, I know what that does. If you get into higher level languages, it's easier to read the code. It's more evocative. It's more like English, so it's easier to read the code. You'll see fewer and fewer comments as you get to higher and higher languages. Also, you'll see fewer comments if you're on a team that everybody is as good as everybody else. But in assembler code, lots of comments. Right, the right motor power level. Oh, RMP must stand for right motor power. LMP, left motor power level. Oh, cool. So what's happening here is there's left motor power, right motor power. They must be controlling motors. The neat thing about this, these registers, these variables, they control motors directly. There's some piece of hardware here that if I write a number to this place, it turns on a motor. This is where computers control stuff. They write numbers to hardware, and it comes out as an output, and the world changes. Okay. The next layer up from assembler code is code that is compiled. This is what's called high-level languages. We used to call them high-level languages. Let's take an example of what a high-level language is. Your high-level languages are basically C or JavaScript. So we're graduating up from numbers. Now we've got words now in our assembly code. I want to deal just with stuff that looks as close to English as possible. So at a high-level language, I've got different building blocks. In machine code, I've got numbers. I've got instructions and operands. I've got operators and operands. So I went from numbers to machine code to assembly code to high-level language. What are the building blocks? What are the Lego blocks in a high-level language? Building blocks are variables, statements, and then tests, initial tests. And loops. Those are the building blocks you've got to work with. So what's a variable? If I say sum equals 0, semicolon, that's a simple statement. And that statement works in JavaScript or in C or in any number of languages, Perl. This kind of simple statement is very common in functional languages. Sum here, this word sum, represents something. I don't know, apparently I'm adding things together. I'm summing things up. If you have an equation like x equals a squared plus b squared plus c, a quadratic equation, this is something that is solved for values, and you end up graphing it, right? This is math. It's a little different in programs. We're not solving for a solution. We're not ending up with a graph. We're doing something. Just like I said, the simple operators in machine code are things that the machine is supposed to do. This is an instruction. It says take 0 and put it in this bucket that I'm calling sum. It means sum gets the value 0. I know this is real basic stuff, but 121 is where we introduce programming to people, so we're going up from the bottom. Please stay with me. If you want to take a nap, please, put your head down and try not to snore and buzz the rest of us. You can do math in statements. So you can do things like sum equals sum plus count, semicolon. Don't forget your semicolons. Don't forget your semicolons. Now what's happening here? Well, I took whatever the old value of sum here, and I took whatever's in here, I added them together, and I put them over here. So, if you were a mathematician, you'd say, well, obviously this is wrong. You can't have something equal to something plus something else. They're not equal. So it's not an equation. It's not like math. It's an instruction. It's do this and then put it here. Do this and then put it here. That's the critical thing about a programming statement and how it's different from a mathematical equation. They use the same symbol. It's not the same thing. Now there are simpler ways of writing this. And you'll see this in JavaScript. You'll see this in other languages. If you're just adding something to a sum, if you're going through a loop and you're adding 1, then adding 2, then adding 3, adding 4, you do that a lot. One of the things you'll see in programmers is they hate typing because they do it all the time. It's just a time waste. And things can get a little funky because people will make short variable names because they don't like typing long variable names. That's not good. You should have variable names that mean what they are. But there's no reason to repeat yourself. So you'll see one of the big principles in the computer business is called derived. So don't repeat yourself. You'll see that principle in a number of different places. I'm going to switch to blue because all my black aren't today. So in some sense, I'm repeating myself here. I'm saying sum is equal to sum plus 1. Why don't I just say sum plus equal? This is a shorthand notation. This is a shorthand notation for this operator. This is an operator. This is an operand. This is a result. These are operands as well. So if I take this operator, plus equals, it means take this thing and add this thing to it, put the result back here. You do this all the time. You do this just all the time. Another thing you do all the time is you'll do something like sum is equal to sum plus 1, semicolon. That's real common. You're going through and you're doing stuff over and over and over again. Most likely it's not sum. Most likely it's count, I'm counting things, is equal to count plus 1. I do something, I add something to a variable called count. Let's say, for example, I'm trying to sign up for 3 classes. Hint, hint. I have a number of classes. Every time I look at a class, I add 1 to the number of classes I've looked at. This is real typical. So we have a shorthand notation for that. Count. You could just say count plus equals 1. Same thing is up here, plus equals. I'm just going to add this to count, put it back in. But even that's too many characters. We do this so often. We have a special symbol called count plus plus. Semicolon. Plus plus just means increment that. Add 1, put the value back. This is where the joke comes from. The guy who invented C++, it's a joke. It's a computer joke. It means I just incremented C. It's just a little better than C. He's a very self-effacing guy. His name is Barnes Shustrow. Anyway, that's computer humor for you. You gotta be an insider. Even then, it's not that funny. Anyway. So this whole concept here is about shorthand operators. So we picked this thing, a variable. We're going to hit it a couple times today. A variable is what? A place to store stuff. Now, usually it stores numbers, but it can store other stuff. We'll talk about that later. A statement is a way of telling the computer what to do. Make this variable equal to this number. Do this with this variable. So a statement is a way to tell the computer what to do. Statements are usually ended with a semicolon. In JavaScript, in Perl, in C, use a semicolon. There are situations where you don't need them, but there are plenty of situations where you do, and if you leave one off, it fails, and it fails in a weird way, so just throw them in there. There are some languages where they're wrong. You don't use semicolons. Python, Ruby. Just if you see Ruby with semicolons, it means the guy doesn't know what he's doing. He's a C programmer who's in the wrong neighborhood. Statements have semicolons at the end of them. So I want to take a break, because enough of this. And then we'll go through and we'll talk about conditional tests. How does somebody, remember we were talking yesterday about flowcharts? And we said these are things that you tell the computer to do. These are statements. It all connects together. Well, the next thing is, how does the computer decide what to do next? And those are the conditional tests. We'll talk about those. And then we'll talk about loops, where you combine the two, where you have a bunch of statements, then you have a conditional test, and you go around and do it again. So that's what our next little segment will be about.
And that's all.
No, we're going to go further. Your head's going to explode.
I've had a long day.
Well, don't worry. I'm recording, you can watch it later. We've got to get to the functions. We've got to get to the functions. We've got to put it all together in a big basket. And then we'll stop. Honest. You can trust me. I never lie. Except when I lie.